Okay, let's go on. Okay, so our next speaker is Suman Das, and he's going to talk about normal transport in one dimension, the coupled rotator model. So please.
So hello, I'm Suman Das. So actually right now I'm from NCBS, so that's a mistake. Anyway, so let me just remind you about the problem here. So we are considering essentially one-dimensional classical systems. And can you hear me? Okay. We're talking one-dimensional classical systems which have nearest neighbor coupling, and they are translational invariant systems. So the question we want to ask is that whether Fourier's law holds or not. And Fourier's law simply means that the heat current is proportional to the temperature gradient. This is, of course, an empirical law. If this holds, then you can combine it with the continuity equation for energy to obtain a diffusion equation for the temperature or the energy, provided you ignore quadratic and higher order powers of the temperature gradient in the system. And so this is, of course, known as normal diffusion. So how do you check for Fourier's law? So Fourier's law has some simple consequences, of course. For example, in steady state, the temperature profile under Fourier's law is linear. It's of this form. And also you can calculate a size-dependent conductivity, which is of this form. And if Fourier's law holds, you expect that in the thermodynamic limit, it should converge to a finite value that depends on the interparticle potential and also on temperature and pressure and nothing else. So, but it turns out that in one dimension, typically Fourier's law does not hold. For example, what I'm showing you here is a molecular dynamic simulation of the Fermi-Pasta-Ulam chain, two ends of which are at two different temperatures, and you can see. So the left side is at a lower temperature, t equal to 0.1. This is at t equal to 1. So you can see that the temperature profiles are clearly nonlinear here. And since all the curves have collapsed, we are probably in the asymptotic scaling regime where Fourier's law clearly is still violated. And what you see in the inset are expansion profiles in the systems which are also nonlinear. So you could also ask for what is the size dependent of the conductivity in the same system. So this shows you that for different temperatures. So you can see that, okay, the lower temperature case is not as yet clear, but at least at the higher temperature, if you look at the green and the blue curves, you can see that at large system sizes, they scale as roughly as n to the power 1/3. So once again, this is an indication that Fourier's law does not hold in one dimension. So instead of looking at directly at the conductivity in non-equilibrium steady states, you could also ask for equilibrium. So in equilibrium, you can look at the spatiotemporal correlations of all the conserved quantities. So generically, you have three conserved quantities. You have the density, or what we would call the stretch. The stretch is simply the difference in the bond vector, essentially. And they satisfy these three continuity equations. So there are three different currents, which is momentum, which is pressure, and the momentum times the pressure, all of them densities here. And the pressure is simply defined as the derivative of the potential over there. So you can construct a hydrodynamic theory, which has recently been done by Van Byron and Herbert Spawn. So you switch to the normal. First, you can linearize the system. You can expand these currents in terms of the fields, and then you can keep up to linear order terms, and then you can couple these normal modes through this coupling coefficient, which introduces a nonlinear term. So if this were absent, you can see that what you have is a simple linear equation. There are three values for C alpha for the three normal modes, and the values are 0 and plus minus C. So the 0 would correspond to a heat mode, and the plus minus C would correspond to the two sound modes. And with this dissipation term and this fluctuation term, you would essentially get a Gaussian broadening of all the three peaks. And these D and B, these matrices satisfy the appropriate fluctuation dissipation relations. However, when you add this term, that actually changes the behavior completely, and it was shown by Herbert Spawn here that the scaling actually, in fact, because of that term, is not a Gaussian. So let me once again show you what those curves look like. So here you see once again the equilibrium correlations of the FPU chain. So these are actually not the solutions of the hydrodynamics, but they are exact numerical solutions of the underlying microscopic dynamics of the FPU chain. And you can see these central heat modes here. which decays in time, and the sound mode, which both travels and decays in time. Okay, so this is at for these parameter values. So what do these modes individually look like? What do they scale like? So this is the energy and this is the momentum. You can see that the x-axis has been scaled by t to the power 3/5, and all the curves collapse, and so the scaling is clearly anomalous. Not only that, as predicted by nonlinear hydrodynamics, that this follows precisely the Levy distribution. Similarly, for the sound mode, you see that the scaling is t to the 2/3, which is again different from a Gaussian scaling, and also this 2/3 is precisely also the scaling exponent for the KPZ equation, although the KPZ scaling form is something we could not verify numerically. So now the question is, this hydrodynamic theory obviously does not depend on the nature of the potential as far as we can tell. It does not also depend on temperature. It does depend on pressure. For zero and non-zero pressure, we have different scalings, but they are still anomalous. So what about normal transport in 1D? Does it happen at all? Is there any parameter regime for which we can find it? So it's possible to find it provided there aren't 3 conserved fields. If there are less than 3. So I'll be discussing a special case. So, and the case is the coupled rotator model. So here once again we have a Hamiltonian of the same form, except that the potential is now sinusoidal. Okay. So, and the reason for studying this is that there's a lot of previous work, mostly numerical, on it, which find very clearly converging conductivity in the thermodynamic limit in these systems. So, and it has even been claimed that there's actually a transition from anomalous to normal somewhere in the temperature range 0.2 to 0.3. And so anyhow, at large enough temperature, it's clear that the model shows normal conductivity, and this has been found surprising because the model is momentum conserving, and you don't expect such systems in 1D to show normal transport. So if it does show normal transport, if it indeed belongs to a different class, there must be a relatively simple hydrodynamic explanation for that, and the explanation we propose is something like this. Here, the stretch Rx, if you look at it, it's not a conserved variable, it's not a conserved field, because Rx is really an angle between 2 vectors now that is restricted within the cell 0 to 2 pi with periodic boundary conditions, which means that one of the R's, once it crosses 2 pi, it can be reset to 0, and so essentially it jumps to 0 without any of its neighbors being reset, which means that, you know, if you look at Rx, or the summation of Rx is not a conserved field. In the stretch conserving models, for example, the Gibbs weight is like this. So if you have a pressure P bar, so this is invariant under the dynamics because the summation of Rx is a constant, which is not so in this case, which means that R is essentially not conserved, and or you could say alternatively that it is conserved only for P bar equal to 0. So when P bar unequal to 0, the system is inherently in a non-equilibrium state. So you could also ask that, okay, what if I do not reset my R? I mean, I let it wind round. Does it change the microscopic dynamics? Of course, it doesn't. But if you don't do that, then the problem is that this weight, you can see any averages depending on R that you calculate from this weight will diverge, because for R goes to minus infinity, for example, those will have infinitely higher weights. So, and the reason is very simple. The reason is that this term really does not respect the rotational symmetry of this term. So this P bar times R is like an external torque that you're coupling to the system. So, and the system is sort of inherently out of equilibrium when P bar is not 0. Is that point clear enough? Or I hope so. Okay. So, so the upshot of all this is that the pressure in the rotator model in equilibrium is identically 0. So it is important to emphasize that this is different from the case of 0 pressure in FPU type models, because there, although the pressure is 0, the coupling tensors that you had, the G that I showed you and the C alpha that I showed you, they really depend on the first and second order derivatives of pressure with respect to the energy and volume. And those derivatives are still non-zero at 0 pressure. So you still have a non-trivial hydrodynamics. Here, if pressure is identically 0, then those derivatives vanish. And so all you are left with is this rather simple hydrodynamic equation where the current is simply given by the dissipation term and the fluctuation term. And this, of course, has a very simple solution, which is of a Gaussian form, where alpha refers to now just these 2 quantities, momentum and energy. Unfortunately, we cannot determine D directly because the fluctuation dissipation does not impose enough constraints for us to determine all the t's independently. So this is something that needs to be found numerically. So this is once again a simulation of the momentum and the energy modes, and here you can see they're very clearly Gaussian. So the dotted lines are a Gaussian fit from which you can get the diffusivity of momentum and the diffusivity of energy. So we can see that both energy and momentum diffuse normally in this model. Now once we have found these diffusion coefficients numerically, we can use it to predict the conductivity of the system. So for example, of course, like I showed you earlier, using Fourier's law, you can show that the conductivity is the diffusivity times the specific heat density. And in this model, the specific heat density has an exact expression. And for our parameters, for V0 equal to 1 at temperature 1, which I showed you earlier, you have this specific heat density. So you predict that the conductivity should have this particular value, 0.5749. Now you can directly determine the conductivity, and you can do it in two ways. One is you can use the Green-Kubo formula. So Q tau is the heat transported in time tau. So you calculate Q tau square average divided by N, and that should give you the conductivity. Also, you can directly calculate it through non-equilibrium simulations like on the FP chain that I showed you earlier. So once you do all that and then you compare with the predicted value that you get from the diffusion coefficient, and those three match fairly well. So this is the predicted value, this dotted line. The red one is from the non-equilibrium simulation, the blue one from the Green-Kubo formula. You can still see that there is some 3 to 4% difference, and that is because the diffusion equation itself is not exact. It ignores higher order terms in the gradient of temperature, and at this temperature that can introduce these small corrections. So yeah. So let us try to understand this non-conservation thing a little better. So when we're talking of non-conservation of stretch, how do we characterize it? So one way is that when a quantity is conserved, it satisfies this exact identity. Okay, so and since Rx is not conserved, we expect that this object, which we define as ST, that should decay with time and go to 0. So so what should be the decay time scale? So one simple way of calculating the decay time scale is this. It's not an exact thing, but at low temperatures, you can sort of assume each bond vector like a particle which is trapped within one well of the sinusoidal potential. And at low temperatures, its escape from that one well is like a Kramer's escape. And at low temperatures, that escape time should be given as exponential of delta E by T. So this time scale is really what gives you the time scale of decay of this quantity. So we expect that ST should go as exponential of minus T by tau, with tau exponential to V0 by T. So once again, we check for that. And firstly, we see that it is indeed an exponential decay. And also, when you plot log of tau versus 1 by T, you get this sort of a curve showing that it is indeed exponential of 1 by T. And the slope is supposed to be 2 for V0 equal to 1. We get 1.82, which is reasonable at this level of approximation. And so you can see that the dependence of temperature of this quantity is very strong. So exponential 1 by T means that at low temperatures, the really diverging time scales of relaxation in the system, which means that in any typical non-equilibrium simulation, you would essentially see not a normal but an anomalous conduction behavior. So that is probably what underlies the report of normal conduction at low temperatures in previous studies. Okay, so what really happens at low temperatures? So if what we're saying is correct, then we should expect that at low temperatures for long enough times, the particle is trapped near the bottom of the potential well. So you can essentially do an expansion of the sinusoidal potential. And that expansion, you keep up to the first stable term in the system. So this is, of course, just a harmonic term. You want an anharmonic term. So the first stable term is this. Okay. So if you consider precisely this potential, then this is just like the FPU chain, which has 3 conserved modes, and it should satisfy the predicted scalings from nonlinear hydrodynamics. And so the system is also at 0 pressure, so there should be a Levy 2 by 3 heat mode and diffusive sound mode and all that. And if you can see that the behavior of the rotor model at low temperatures satisfies precisely the scaling obeyed by this model, then we know that we're probably on the right track. So here I show you some of the data from these two simulations. So this is for the rotor model, and this is for the the nonlinear model that I showed you, which is the expansion of the cosine. And so you can see that they follow a scaling t to the power 0.62. Well, we expect 0.66, but it's close enough because up to these times, you only get the scaling. You need longer times to see the better scaling. And you actually compare it. This dotted curve actually gives you the comparison with the anharmonic model. You can see it's pretty close, a small difference, but that would disappear as you include higher order terms in the expansion of the potential. So this is reasonable. Okay. So let me go to the conclusions quickly. So it has so far been believed that translational symmetry has to be broken in order to obtain normal conduction in one dimension. But the coupled rotator model was surprising. So what we show is, what is important is not translational invariance, but the fact that it does not support a finite pressure in this case. That leads to all the derivatives of the pressure and therefore the coupling coefficients in the nonlinear hydrodynamics to be 0. So, and in this model, momentum as well as pressure, both of them diffuse normally. And so this is probably the first time we have seen normal diffusion of momentum in a one-dimensional system. And also, sound modes are absent in this system because momentum and energy are the only conserved quantities, and both of them diffuse normally. And also, the relaxation time to asymptotic behavior, it has a very strong dependence of temperature, like I said, which explains earlier reports of anomalous conduction. So there is a more general conclusion that can be made from here, is that generally you have 3 conserved quantities in a Hamiltonian system. In one dimension, you have energy, momentum, and density. So when either energy or density when either momentum or density they are not conserved, you would expect energy to diffuse normally. So that gives you some general hydrodynamic criteria for normal transport in one dimension. It's something that people have looked for a long time. But in terms of conserved quantities and hydrodynamics, this is probably a general solution to the problem.
Thank you very much. Are there any questions or comments?
Yes. Yes.
So it's almost time. So let's thank the speaker again.